Okay. Yeah, for the second part, I just want to give a small overview about the things we did last year. So basically, there's nothing spectacular in it, but it's just, yeah, to give you a small update. So first of all, we reworked our actuator control device, which is responsible for the grabbers and for all the tiny sensors, let's say. So everything except the camera and the motion device. And one thing why I want to present that one is because there are currently a lot of IoT devices around, and we tried to use one of these IoT devices to have more comfort and have easier maintenance when developing with our robot and when we make changes. And therefore we use this board is called BeagleBone Blackboard. Maybe some of you know it. And one interesting reason to use it is that it is able to run Ubuntu on it and to have a standard Ethernet connection. So we can use all our stuff that we use on the robots too within a ROS middleware and communicate with Ethernet. And this is, yeah, easy to maintain. And the BeagleBone Blackboard, in comparison to the, let's say, Raspberry Pi, has the advantage that it has more digital I/Os and, yeah, so stuff that we need to plug in as much actuators as possible. Yeah. One question that we cannot answer yet is whether it is robust enough for the RoboCup domain, especially whether, I don't know, electrical issues make it break, or I don't know. That is something that we will see in the next tournament, I guess. Just for completeness, these are the devices that are connected. So it's there's an inertia measurement unit that has a gyro, an accelerometer, then we have a light barrier, tiny motor drivers that power the grabbers, an optical flow sensor that we presented in the workshop last year to detect the rotation of the ball, which is still not in a state that we would like to have it, and one servo motor that selects the shovel for the kicking device. Yeah. Another work that is in progress is one of our students is working on a new kicking device, not on the kicking device itself. It's he's developing a board that charges the capacitor for the electrical kicking device. I guess all of the teams are currently using an electrical kicking device, right? Yeah. And I also guess that most of you use a step-up converter to charge the capacitor. Yeah, probably. And his idea is to use an AC transformer to step up the voltage. So if it works, then it would have the advantage that it can change the capacitor more quickly. We have a galvanic isolation, so between the primary and the secondary side. So if something crashes on the right side, the left side will have lesser effect. So we have more safety, and hopefully it's more energy efficient. At least that's what my student told me, so I'm not too good in these kind of electrical stuffs. One definitely disadvantage will be that it has more weight, and we have no experience on that area. So we are not quite sure how we have to dimension other parts that we need to make this conversion work properly. So this is again something where we will see hopefully next year whether it's a good thing to use or not. But is there any other team that ever tried it or any experiences with it? So it's my question to you. Okay. So maybe next year you will, at the next workshop, we will have some update on this one to see whether it's good or not. We also made something in our localization. I assume that all of you know the particle filter approach, which is basically some kind of template matching where you have some hypothesis on the field, and you match whether the line points that you saw match on the field that you have saved in your config or somewhere else. And another approach, which is also very well known, is this gradient descent approach from the triboards, where you just assume that you already have quite a good position, and then you compute the gradient of this position with respect to the error that you have in the same error landscape as in the particle filter, as for the particle filter. And our idea was that we combine both. So for each particle, we make some gradient steps and optimize them to have a more precise position. So we can use this to have less particles and still have the same precision as would have with a lot of particles. So the good thing about that is by adjusting the number of particles, we can have a global localization, but still have the precision of the gradient approach. And another advantage of the gradient approach is, of course, that it needs less computational power than the particle filter, because you just have some steps, and it's usually sufficient to find your position. What we are currently working on is on how we want to select the number of particles and the number of gradient steps, because usually if you have a good localization, you require only a few gradient steps and less particles. And if you have a bad localization or you're completely lost on the field, then you want to have more particles and less gradient steps. And but our question that we have not yet answered is how we adjust these two parameters against each other. And for that reason, we don't have any numbers yet on whether it is better than either of the original approaches. Yeah. And the last thing we are working on is also, again, a student project where we try to make the obstacle detection with ASUS action cameras with a depth camera, similar to the Kinect. It's a very simple idea. We just detect the ground plane. Then we compress the data in a voxel grid, which is more or less, a voxel is nothing else than a pixel in a 3D space. And during this step, we also just throw some uninteresting points away. And then we can remove the ground plane, and the remaining objects are assumed to be obstacles, so either teammates or opponents or the ball. And this looks like this, but on this slide, okay. On my laptop, it did look better. So on my laptop, you could see that here and here are obstacles in a different color. Yeah. Okay. Bit hard to see. Hmm?
The green is the ground plane, and where you only see black spots, there are obstacles in red spots.
Yeah.
And the blue one? That's the wall.
Yeah.
Side of the field, the blue one on the left.
So we would detect the blue one also as an obstacle in practice, except we would. It's also still in progress, but probably we would throw away obstacles that are bigger than an opponent could be. So, yeah, that's it. So I just wanted to give you a small roundup on the recent things that we did. Any questions?
Lots of things going on, right, actually.
Yep. Questions?
Do you have any preliminary results on the charging system based on the transformer?
Not yet. It's not
yet.
It's completely conceptual yet.
Okay.
So we have also problems in finding a good transformer that has a proper relation between primary and secondary side Windungen. Yeah.
Number of coils. Yes.
Yeah, exactly.
Right.
So,
okay, and on the other things you are working on, are there any preliminary results that you'd like to?
no,
Oh no, it's still ongoing work, no results yet, right?
no results yet, yeah.
Okay. Are we expected to have some of this stuff working in the next tournament?
Yeah, actually that is the goal. I mean, for the charging system, I'm not quite sure, because this is very experimental, and the next tournament is already, it's only 6 months 7 months, I don't know. So only a few time, and we also have, I mean, the other thing that we are doing, of course, is since you all know that we ported our stuff from C# to C++, so we have to re-implement all our behaviors, just standard situation and so on, and yeah.
Just a couple of few questions about the Kinect, because we've been doing some trials also with it. First, do you distinguish the ball between the obstacles, or it is something already known? Because you said the blue was the ball and the other one are obstacles. And you distinguish between them?
The blue was the ball, not the ball, but the
Goal, okay, the goal. So an obstacle is an obstacle, okay.
yeah, and I guess we can see whether it's the ball or not based on the
The signs. And the other question is, from the experiments we've done, I think up to 4 or 5 meters you didn't get any more information. It's probably the same that you get.
Yeah.
So around 4 or 5 meters you cannot get some reliable information.
Yeah, this depends strongly on the light conditions. So in Istanbul, for example, this was the last time where we evaluated the data from the Kinect at that time. It worked almost up to the midline of the field. So what's this, 9 meters? So it was on the Kinect was on the goalkeeper, and it's like 9 meters. This worked. But we also had areas in our cafeteria, it works like 1 meter.
Yeah, it depends
So
on
it's even worse.
I was just thinking, right, can you, because you have the depth, but you as well have the normal image, use the normal image that you can see with color where the ball is, and then map that one on the depth?
That's something that we've been trying to do. It's filtering color within this web from Don Jose. We filtered the problem we have is that you have several balls that are not good balls coming from noise that is there. So we're filtering it with the 3D. That's the opposite. So we say we might have balls on this position, but these one are too far away, so probably this is the one that we are missing. You can do it, but you have limitations because it's up to 3-4 meters. 5 maybe, that's the maximum you have. And we are still working on that. Actually, the last thing we were discussing about it was to try the new Kinect. I think the distance is the same, but it probably has larger resolution, so we have to try to work on it. And there's also a problem that might come up is there are some interference between Kinect. So if everybody starts using Kinect, if you make robot just in front of the other ones, they will not see anything. But the worst, I think, has light illumination. If you have lots of light, then you just forgot it. I was not in the last that we've been, but I just remember Jose told me, I think it was in Villarreal, that forget about Kinect because you cannot see anything.
You should not underestimate the standard directed camera. So if you just search for balls that are from the, if you are the goalkeeper and you just search for balls on the field, then the directed camera is the best thing.
But the idea was to combine, I think.
Yeah.
Learn about trying to combine, not just choosing one of them.
Okay, any more questions? Yes. Thank you so much. Round of applause for Carpe Noctem.